So I just want to give kind of an overview of where we are right now. We've pretty much finished up chapter 23. Okay, so everything that you need to know about Faraday's law we've talked about in order to do the homeworks that are due on Friday and on Monday. There are some things in the chapter 23 which we're not going to talk about too much. If you are in electrical engineering, I recommend that you actually read section 23.6 on inductance, which is basically just using Faraday's law in sort of circuit applications and looking at how if you have changing currents in a circuit, then because currents make magnetic field, you're going to have a changing magnetic field, which then creates changing electric fields and how that affects circuit analysis. And so that's a useful thing to look at if you're going to be going into any applications involving circuit design or various other electronic applications. So you might want to read through that. There's another discussion on energy in electric and magnetic fields. We'll come back to that in the next chapter, so we will say something about that a little bit later. And then there's an optional section in the end on basically alternating current circuits and RL circuits, circuits where you have resistance and this quantity called inductance in a circuit. So if you're interested, you can read through that. But basically, we are done with chapter 23. So we're going to start something new today, chapter 24. And 24 is kind of the climax or kind of the highlight of this entire sequence, this entire course. I want to just remind you of something that if you were here on the very first day of class, I think we did this on the very first day of class, you may have seen, but I'll just show it to you again. We have this device here, which if I plug into a wall outlet, and I have here just a light bulb connected to two copper wires, okay, by alligator clips. Okay, so it's really just a light bulb and two bare wires. And if I bring it near this device, the light bulb lights up. And I bring it away, and it goes out. And I can bring it near and turn it like that. It goes out. And I turn it that way, it comes back on. And if I bring it over here, it goes out, or at least it gets dim. It goes out when if I do that. Bring it over here, it comes back. Here, now it's a little bit, it's dimmer at least. Okay, and then bring it over here, it's brighter. And so we showed this on the very first day of class as just kind of a teaser, and we said that it would take the entire semester to build up what we need in order to explain what's going on here in explicit detail. And we're finally getting to the point where we can do that. And we're going to start talking about today, well, hopefully we'll get there, but the basic idea of chapter 24, it's on radiation, electromagnetic radiation. And I want to start the discussion by, again, just summing up where we've been. We've past couple weeks here, we've looked at patterns of electric and magnetic fields in space, and we saw some new equations, kind of fundamental relationships, which relate fields to geometry, basically, and charge and current. So we saw Gauss's law, which says that the pattern of electric field over a volume, which we can calculate using this quantity called flux, E dot n hat dA over a closed surface, is related to the charge inside. So it's equal to Q inside divided by a constant. We saw Gauss's law for magnetism, which says that the magnetic flux over a closed surface was equal to 0. Okay, so there's no magnetic monopoles, this is telling us. We saw Ampere's law, which says that the magnetic field pattern over a closed loop, so if we're integrating not over an area but over a loop, this path integral of the magnetic field tells us about the current that's passing through that loop, so the enclosed current. And then finally we saw Faraday's law, which tells us about the pattern of electric field over a closed loop, namely this curly electric field, non-Coulomb electric field. If you integrate that over a closed loop, that is associated with a changing magnetic flux through that loop. So the negative time derivative of B dot n hat dA. Okay? These four equations are called Maxwell's equations. And so they were discovered independently, but James Clerk Maxwell in the late 1800s was the first person to kind of encapsulate them all, put them all together, and to realize that these four equations, along with the electric and magnetic force laws, so if you have these and the electric force equal to Q times E, magnetic force is equal to QV cross B, they basically encapsulate everything we know about classical, non-quantum, but classical electric and magnetic fields. Okay, so all of electricity and magnetism is summed up in these equations. We could have written them on the board the first day and be done. And said, okay, we're done. Except that it requires a lot to understand what they mean and to apply them to various situations. But there is, in fact, one problem. In fact, it's not the complete version of Maxwell's equations. There turns out that one of these is incomplete. And it turns out that Ampere's law, as it's written here, isn't quite right. And again, it was Maxwell who was the first one to realize this. And the way you can argue it is this. Let's say you have a wire, okay? And there's a current in it. And Ampere's law says that if you imagine a loop surrounding that wire, so this wire is going through this loop, so I'm kind of drawing it in perspective here, then the enclosed current is going to be thought of as if I imagine a surface that was stretched over that ring or that loop surrounding that wire. The enclosed current is the amount of current piercing through that surface. Okay, so there's a current piercing through that surface, which tells us that if there is an enclosed current, we're going to get a curly pattern of magnetic field around the loop here. Okay, we've seen this before. The ambiguity is that it turns out that's not the only surface you can think of as being bound by that loop, and you have to use a little bit of imagination here, but I don't necessarily have to have the surface stretched over the loop. I could have a surface that's bound by the loop. It could be in any shape. For example, it could be sort of a bowl shape. So here's a surface that kind of stretches out, and you can imagine the ring here as the mouth of a bowl, okay, or some like a vase-looking shape. Or if you're blowing a bubble, remember we made the analogy of a soap film and a bubble. If you're blowing a bubble, before the bubble actually leaves the little ring, it kind of blows outward. And so there's the edge of it is bound by the ring here, but the surface is kind of stretched outward. But that's okay because eventually the current does pierce through the surface. It's just not where the ring is, but it does pierce through the surface. But there's a problem if you have a situation like this. Let's say we have a current and a capacitor, so a parallel plate capacitor. Well, I draw my loop around this current, and again, if I think about that surface, there's going to be current piercing through this surface, so I definitely have an eye enclosed, and I'm definitely going to get a magnetic field going around that loop. But if I imagine the bowl shape now, and I'm going to stretch this bowl-like surface around 1/2 of the capacitor. And again, that's a completely legitimate surface to think of, bound by that loop. Is there any current piercing through the bowl? No. Is there any charge that flows across the capacitor? No. No. So we've got a problem, because now it says that I enclosed is equal to 0, right? But we still got this magnetic field. I mean, just because we've changed the shape of the bowl doesn't mean the magnetic field goes away. So we've got a problem. Something's wrong with Ampere's law. And Maxwell realized that you have to make sort of an analogy to Faraday's law. In Faraday's law, it says that if you have a magnetic field that's changing, you get a curly electric field. And so what if the opposite were true? What if you have a changing electric field and you get a magnetic field? Well, let's look at the capacitor here. What's happening if a current is running onto the capacitor? The charge is building up on the plate, right? So we have positive charge here, negative charge here, and this Q is increasing. What's going on inside the capacitor? Well, in fact, it's a Coulomb field, right? Because there's just charge on the plate. So we have inside the capacitor an electric field, right? And the electric field is pointing to the right. Okay, so I have an E inside that's pointing to the right. What's happening to the electric field? It's getting bigger. The electric field is getting bigger because we're charging up the capacitor. More and more charge means more and more a larger and larger electric field. So here's a case where along this deformed bowl-like surface, we have an electric field that is increasing. And so Maxwell realized that we can get a curly pattern of magnetic field, this is B, if we have a changing electric field, just as we got a curly pattern of electric field if we have a changing magnetic field. And so Maxwell realized that Ampere's law has to be corrected, and we have to add a term onto it. And the term we have to add, and I got to make sure I get the constants correct here. The term is mu naught epsilon naught, so this magnetic constant and this electric constant, times a time derivative of an electric flux through that surface. So E dot n hat dA. Okay, so let's just say this one more time. This is an electric flux, electric field measured over a surface, which is what we've got inside this capacitor. We have a derivative with respect to time. So if the electric field is changing with time, we're going to get a curly pattern of magnetic field. Okay, so there's sort of two ways to produce a magnetic field. We can either have a current or you can have an electric field that's changing. Okay? So this is the complete form of Maxwell's equations. Gauss's law for magnetism. Sometimes this is called now the Ampere-Maxwell law because Maxwell added the correction, and Faraday's law. Those four those four plus the force laws, again, sum up everything we need to know about electromagnetic fields. So we have this symmetry here. We have electric field changes, we get a magnetic field, or we have magnetic field changes and we get an electric field. And this is also kind of suggestive. It says that, well, every pattern of electric and magnetic fields in the universe has to obey these four equations. If it doesn't obey these four equations, it's not possible. Okay, it's an impossible pattern of electromagnetic field. So maybe there's a possibility to have an electric field that's changing, which creates a magnetic field that's changing, which creates an electric field that's changing, which creates a magnetic field that's changing, and have sort of a self-perpetuating, changing electric and magnetic field pattern. Okay? Seems suggestive, again, from this symmetry between the Ampere-Maxwell law and Faraday's law. Well, if we imagine we're going to play a little game today, which is basically if we can imagine such a pattern and then applying that pattern to each of these four equations and seeing if it satisfies each of those four equations, then we know it's possible. That's the name of the game. Okay, any pattern of magnetic and electric fields has to obey these four equations.